All right, here we are. It's Thursday. It's 8 o'clock. We're ready to go. We're going to talk about brains today. Why wouldn't you? Thursdays are the best day to talk about neurology, to talk about health, getting people feeling strong. We had some homework from last week about dropping in the chat first thing and just drop something good in your life. Drop a little positive help for other people, something you're happy about today, something you're thankful for. And that's how we'll start the day. We'll start it off with a little fun, and then we'll get into our content for the day. We're almost like a real get up over here. We've got a couple different segments we're gonna do. Bring in a guest, and then we'll talk about some fun. Where, as you see, the title is "Are We Wrong About Autonomic Function?" So, okay, we got our looks like streams up and running. Hopefully, I got to take a quick peek here, see what else we're working. Looks like we're streaming. Looks like we're streaming. Good. Okay. Well, let's get after it. Eileen from the Jersey Shore. Lucky duck. Love it. Enjoy it. Hope you're enjoying the waves. Decent says hello, class. Doru. Hello, hello. Is that how you say that? Doru. Okay. All right. So we're going to have some fun today. I'm not sure why I've got a little caution sign on my stream, so I'm not sure what that's all about, but we're going to go for it anyway. All right. So yeah, any good news you guys have for each other in the chat, just to bring up everybody's day, we would love it. Never get up, always hope, love it. Julissa, good to see you. Big Erm, when will there be a cure? How long do we have to suffer? Well, it depends on outputs. Also, hello. Okay. All right. So here we go. Just today, we got a new person for you guys, which is fun. Not new to me, not new to the clinic, but new to the broadcast, which will be cool. So it's taken us about a year to go ahead and get her on the stream, but here she is. So this is going to be Dr. Alexa Tenwalde. We call her Tenny Wild, but she has been with us just over a year in the Kaiser Clinic Ninja Doctor training system. And she's going to be she's going to be here today to talk about a little good news, how a little different case. So I'm going to bring her on. She's going to share it. We're just going to walk through a quick data set and just check in. So here she comes. Here's Dr. Tenwalde. Welcome.
Hello. Hello.
So, yeah, taking us a year to finally convince you that this is a safe space.
I know. I've been begging to get on here for so long. You finally allowed it to happen. I'm so excited.
Yeah, that's something like that. All
Yeah.
right, so you want to share? We got some hellos. I don't know if you can see
I
the stream
can,
here.
yes.
Leah says hi. I took a picture of her t-shirt today. We'll see if we can get that on the stream as well. But I'm going to turn it loose to you. We're going to share your screen and then just walk us through these findings here. Walk us through what they mean, why they're hopeful for the crowd. So I'm going to let you have it. Off we go.
Okay, awesome. Yes, I just really wanted to share some of these data points because they were so exciting and we were celebrating so much in the clinic the last couple days over this. But I wanted to show for this patient, we have her initial tilt exam. And a lot of you have probably seen these charts on previous streams, so you have kind of an idea of what these numbers mean, but I'll still kind of walk through that a little bit just to make sure we're all on the same page. But this is a patient that came in with some like severe fatigue, dizziness, like pre-syncope type symptoms upon standing. So this is our bread and butter that we see quite a bit in the clinic. And yeah, so here's our initial exam with her. This is our first couple minutes of supine and our heart rate here. So we can see we're at like a pretty decent heart rate coming through here. We went over that ETCO2 last week on the stream. Super happy we got into that. And then in these darker gray boxes, this is when we actually get into orthostasis. This is where we have that 70-degree tilt. And we can see on this initial exam, these are the two columns we're really looking at here, the mean percentage change that we see when we go upright against gravity into orthostasis. We want these numbers to remain ideally above 85%. So that's at 85% of the mean velocity that we can maintain compared to baseline. So we can see these bolded numbers here. She did not quite maintain that on her first tilt. So as we're measuring minute by minute here, we can see there's quite a bit of fatigability to it. She's dropping down into the 70s, down to a 69 down here. This row here is where she did some dual tasking. We gave her a math equation to do. She did really well with that, and you can see that right after we got done, fatigability crashed back down again. And then after that initial exam, we got to work. And this is a patient she's just so eager to get to work every day. We were loving the energy. We're getting a lot accomplished. And after 7 days of treatment, we said, okay, let's take another look at this tilt exam. So right away, you can see from this heart rate, minute by minute, like compared to our initial, where we jump up into the 120s beats per minute. Now on our re-exam, we're hanging down here in the 80s. This was super great to see. But previously, the reason that we were getting a big increase in this heart rate was because we were trying to make up for not having enough of that cerebral blood flow. Now I'm going to move the chart over to this side here, and we can see, wow, these numbers blew us away. So immediately right off the get-go, right out of the gate, minute 1, she is maintaining that blood flow, and she does not give it up the rest of the test. We were so happy with these results. She's maintaining that velocity of the blood throughout the entire test. There was not that fatigability at the end of it either. She maintained it strong. And then also with that, we didn't have to have such a big compensatory heart rate increase. And so this is a good sign into showing that we're maintaining our blood flow. I also really wanted to point out too, those ETCO2 levels, just because I know we talked about it last week on the stream. So her initial exam here, we can see we're dropping these numbers down into the low 20s. Far too low. After 7 days of treatment, I think we still have improvements to be made, but now we're hanging out high 20s, low 30s. This was also just super great to see. We were all celebrating. Once we got out of this tilt exam, I just knew we really wanted to show this on the live stream, show the world. We're all celebrating, and yeah, I think these are some really fun numbers to share with you all. So yeah, what do you think, Dr. Kaiser?
Awesome. You got the first one in. And I also think
Mm-hmm.
that I went to go respond to one of the chats, and then it kicked me out of chat, which is super fun. So I'm officially logged out of the chat, trying to get YouTube to verify that I am here. So I'm supposed to be opening my phone and clicking number, whatever this number
Lovely.
is, and it's not working. Anyway, so yeah, the thing that really excites me is so many people. It's just it's curious, right? They're wondering like what is going on over there, and it's just an insight into that progression. So we talk so much about cerebral flow, right? But then,
Mhm.
like, how does that translate to this thing everybody's worried about with heart rate? And then you can see just really clearly where the overlap is, right? So if you can actually make the system more efficient at distributing blood, then the heart doesn't have to work so hard. And then you can see that in the outcomes. And that's what Dr. Tenwalde showed here. Great job, first go around. I love it.
Phew, thank you.
Um, yeah, so it's really cool. And the important part is we talked about this a couple weeks ago, but I think it's worth sharing again. Is just this idea of this is kind of like the baseline substrate for just being healthy. So if we can think about, we talk a lot about not just POTS and dysautonomia, but also, MECFS and problems where it's just really hard to get any energy running, right? And so oxygen, glucose, they're like the substrate. That's it's like what the ingredients are for making energy. So if we're having a hard time being able to continually give the brain the ingredients, um, then it makes it really hard to run it. You can't run the car on empty. Same with your brain, and so we focus on that, and then you want to use that in order to let the body heal. And I think that part's important. Is at the end of the day, that's what we're trying to do is put in the right conditions so that the body can heal on its own. Like we're not in the business of healing people. Bodies heal, they heal themselves, right? That's where the process happens. It's not from the exogenous part. So we're just trying to create an environment where they do, and that's the magic of it. So it's worth talking about. I'm going to take a sec, Dr. T. If you want to say anything, just love on the crowd or anything. Can you see the chat? And you want to respond to some chat real quick while I try to see if I can
I
get mine up?
can see the chat. It's a lot of
Okay.
very warm, welcoming. Love to see it all.
If you want to pull
Hello.
them up, you just click them. I don't know if you can do that, but I'm going to jump out real quick and see if I can get back on. Otherwise, I can't see the chat. So I will be.
Okay. Okay, so let's see. Hello from Leah. Yay. Hi, Amy. Eileen, hello. Hi, Susan. Nomad over normal. Great to see you, eh? Nice. And Christy Lee, hello. Hello. Ooh, one of these questions I can probably answer here. So there's a question that is asking, will traditional tilt exam have these spreadsheet data points? And I think that's a good question because in the clinic, we do often get patients that come in that have maybe had a traditional tilt done in another clinic. And some clinics do, they do a great job of measuring certain data points. Maybe you'll get those data points. Uh, but I think one of the bigger things that we maybe don't see in a lot of other clinics is measuring with that transcranial Doppler. So getting that mean velocity blood flow is something that I think really sets us apart for when we're getting the full picture of all of this. Um, so maybe that answers a little bit of your question, but yeah, welcome back, Dr. Kaiser.
Yeah, we got it. I
Hello.
got chat again. It's great. Yeah, thanks for taking that question. And I'll take it a little step deeper. So they typically
Yeah.
don't cover these, although that's kind of like the purpose of why we're here, is
Mm-hmm.
to maybe try to see if we can cajole, is cajole a good word?
Oh,
People into starting to adapt some of these techniques. So that's kind of our hope and our prayer. And then in addition to the mean arterial pressure or excuse me, the transcranial pressures, they have to be coupled to what we look at with the end-tidal capnography because those two things they're kind of like tied together. You can't really understand one without the other, which is why they all have to be in there. Same time, same bat channel. Cool. Well, thanks for doing that. I appreciate it. We're going to stick around. We're going to talk about a little bit of just some, today we're going to talk about basics of autonomic, like physiology, which I know I say that word and that's not everybody's favorite word, but it's like the understanding of what it all means and what it all does, because I actually think that sometimes it's skipped and it gets confusing and we kind of don't think about it in a way that's useful. So, Dr. T, if you'd like to stick around, you're welcome to. I can see you've got your big map and bookshelf behind you. I don't want to
Yeah,
prevent you
thank
from.
you.
So, I don't know if you guys know this, but Dr. T, did you build that bookshelf on your own?
Not on my
Recommend?
own, not by myself. It was a little bit of a team effort for sure, but um,
But it's not
yeah,
just you and
it took
IKEA.
not just me and IKEA. It took like 8 months from scratch. Yeah, absolutely.
Very cool.
Hmm.
All right. Well, I'm going to pop into this. You're welcome to hang out. Enjoy, everybody. I see some questions popping in. We'll get to those after I share some stuff. And the reason I share some stuff on the front end, just so you guys know, number one, we want to share the cases because like it's helpful to just see other people that are winning. So you go like, well, maybe I can too. Because I think there is more opportunity to win out there than people kind of give credit for. So let's just show it. And we've decided to make that commitment to just showing it now. Um, the reason, and it takes a little bit of work. So thank you, Dr. T, for getting that all done. Okay, but the reason we're going to start with a little bit of learning first is because it helps us get a little, just like a little climb up the hill of our knowledge base, which makes it easier to kind of understand where we're going and kind of is, empowers you guys to help be able to think about what's going on, how to make decisions. If you're a physician on the stream, maybe some things to consider that you've thought about in different ways, and that helps us move the conversation forward together. So off we go. I'm going to share my screen now. I'm going to pull this chart down. Thanks for sharing. Okay. And then we're going to put up this one. So this is our shirt from today. Don't get on my nerves. They have enough problems. Thank you, Leah. Hopefully you're still on. Great shirts every day, by the way. We could have a photo for every day, but I was lucky enough to get this one. She was very kind to be able to share this for everybody. In our beautiful, hey, by the way, it's mid-September and we've got how it was 80 degrees here in
It
Michigan,
was
yeah?
80.
I
Yeah.
mean, we are in bonus time because that is not always true, and I'm thrilled about it. So off we go. So today, here's what we're learning about. Thanks for the cameo, Liam. We're going to learn about, we're going to say it in the way like the academic titles, mostly because this is the way I presented it before, but we're going to use normal people words because it's way easier on everybody. So the autonomic nervous system, the regulation of body functions. We call it the autonomic system because way back when people realized, huh, this is kind of like how we control all the automatic stuff. And this is an old document out of, I believe is this Langford's book? I might be getting that name wrong. I apologize if I am. But basically, this is the drawing. So we've got kind of your head, your brainstem into here, and then we get the cervical spine and the thoracolumbar spine, and then the sacral spine. And this is the spinal cord. It says the general plan, several parts of the autonomic system, has been that the thoracolumbar or the sympathetic system supplies nerve fibers to all regions of the body, while the tectal, bulbar, and sacral systems supply to special regions only. And this is kind of how it was all started because of the way the nerves were organized. That's it. Not really based on function, just based on where the nerves came from. So they cut them open, look back, trace them back through, back to the spinal cord. And this was the jam. This was genomics of the time, right? So these people were celebrated, parties in the streets, roses at their feet. You get the idea. So that's kind of where we started from. And then when we progress it out, let me see if I can make this a little bit bigger here. Let's pop us in this way, cover style. All right. Oh man, I didn't realize I did it like this. Okay, so we've got here. You can think about it in two ways. Autonomic system does all the automatic stuff, but we can also think about it in different time frames. So the basic split is like short term, long term, right? So short term stuff, fluid matrix of the body. What does that mean? That is what we talk about all the time with like blood volume, but also what is the blood made of? So like we got the right amount of stuff dissolved in it. So it's like back in the day, my mom, Tenny, I don't know if you're old enough for this, but my mom used to buy the orange juice concentrate
Mm,
that would live in our
yes.
freezer, little Minute
Yeah, the
Maid,
little
looked like
frozen in the
a,
tin can.
yeah, it looks like it could have crescent rolls in it, could have juice in it. We
Hmm.
don't know. It's
Yeah.
got frost on the outside, hard to tell.
Yep.
Anyway, pop that baby out, boom, that ice right down in there, and then what we'd have to do is you just pour water in, mix it up, and then it's the right concentration, right? And that's the way our blood should look. Like it should all have the right concentration of all the goodies in there. And then you get my mom who sneaks in after I make the orange juice, and half the orange juice turns back magically into a full container, and now it does not taste like it should taste, and the concentration is wrong, right? So this is what our body is supposed to be protecting against, is this dilution or making it too concentrated. And that's what we're talking about here. So volume regulation, osmoregulation is making sure that the right amount of stuff is dissolved in the blood. And that is also part of our autonomic outputs. And we haven't really gotten into that a whole lot, but it matters a whole ton. It's just not where we've been. So we're going to start trying to dabble in. What do you think, T?
Hmm.
Okay. And then what goes along with that is gas exchange with the environment. So we take it for granted that when we breathe in, it just magically goes into our blood supply and gets dissolved in the blood and then gets shunted around the body, which is pretty slick. But that whole thing is like a lot of little series of processes that have to happen in order for that to work. Um, so an example of this would be like our COVID time, where we would see people that would get more significant lung problems, lung inflammation, difficulty with being able to make that normal gas exchange. So we are breathing, but it's not necessarily translating through the alveoli into the blood supply. And then we see the oxygen levels drop, right? And that's when people get concerned. And so, again, this is another piece of the autonomic system. All right. And when we say short term, oh, we're going a little quick there. Oh, coming back. I didn't realize I made it this way. But anyway, so these things are all happening moment to moment, all the time. There's no real latency to this. And then obviously digestion of nutrients. So that's not only, it's like, what does it mean to digest food? It means that you have to have like a stable system to be able to have the nutrient kind of like interface with a blood vessel wall, and to be able to take what used to be food and move it through the cell wall and into the blood, which is like a wild idea if you really stop and think about it. It's taking your steak from last night, changing the chemistry of that just enough to like squish it through the walls of the bloodstream, just enough so the steak gets through, but not so much so that like the bacteria come through or any viruses come through. So it's kind of a big deal. And our autonomic system is what regulates the quality control of this barrier system, which is cool. And then that translates to how well we can then shift that out to the different cells. Now we've got some oxygen, we've got some glucose, we've got all the goodies, and then now we can energize and build within the system. So, but if these things don't work, then we're kind of like we're in a rough spot to start with, because this is how we get all of the fuel that does all the cool stuff in the body. So without these things, we're in a rough spot. What do you think? Good language there? We're in a rough spot,
Yeah.
T. So that's where we're at. Okay. So, next on the list. Now we've got all this stuff exchanged. We basically took it from the physical world, which is wild. We were able to create a chemical reaction that allows us to take those things from the real world, put them into the blood supply, and then move it around. And move it around in a way that is specific to what is going on. So the way that we move blood around, if you're doing a math test, is different than if you're in a soccer game, assuming that you're playing in the soccer game. Maybe not if you're taking notes on the side, but if you're playing in the game. Okay. So those are two different tasks, right? So if I'm doing math test, what do I need? I need a whole load of energy in my brain and then a little bit of energy in my pencil hand or in my iPad hand, right? So that I can take things from my brain and put them onto paper. If I'm running around on the soccer field, I've got to put a lot of energy into my muscles so that I can ambulate around the field. But since we're in a game, we've also got to like have some direction. We're not just like robotically running around with no aim. You have to be able to think and decide what are we doing to be able to interpret the world and to be able to react within that world. Not just react actually, but predict what's going to happen next so we can go and be part of the game. So the same way we have to have energy directed into the muscles, we have to have the corresponding role happen in the brain. Otherwise, we don't control the muscles, right? So we have to have the brain be able to initiate that whole process, which is just bonkers if you stop and think about it. It's absolutely beautiful. And I think it's worth talking about the things that are beautiful because that's what we're made of. And when it looks like healing, that is the beautiful part, is just how available that process is to people. Sometimes it just needs a little bit of guidance in the right direction. Same way a cast is super helpful if you break your arm, but the cast isn't the thing that heals your arm. You're just making sure that you don't bang it on stuff or get it whipped around so that it forms funny, right? So it's gonna heal. We just got to give it a little bit of guidance in the right direction. And that's what's beautiful about the body. We cannot forget that part. So it's very easy when you don't feel good to ruminate on the things that are not working, but it's also really helpful to focus on, well, I know these things are not working right now, but I know what they're capable of. And how do I get them back to what they're capable of? Okay. All right. Then once we push it all around in the body, then we've got to get rid of it. So, like, we use it up, we burn it up, just like you put gas in the tank, push it to the engine, it gets burned. But then we've got exhaust that comes out the back, right? So you got your exhaust tailpipe coming out the back. We got a tailpipe of our own, and all of the exhaust we either move out through excretion and waste, urination, defecation, but also through breathing, through sweating. So all of these different factors that help us to take that waste and eliminate it. The CO2 we talked about last week is one of the primary waste products of energy metabolism, of aerobic glycolysis. So that breathing component is a really big part of getting the waste out of the system. And as you guys have noticed, sometimes if we're not sufficient at getting the waste out, even just think about breathing, then we see kind of an error or a buildup in the system that doesn't allow us to manufacture that energy as cleanly. Okay. Another one, we got body temperature. Why does temperature matter? So our body is built to run at a very specific temperature. You guys have all known this since you were kiddos, and mom hit you with a thermometer to see if you should go to school or not. And that temperature really matters because it allows us to maintain a pH. And that pH is the acid-base balance within the system. And that acid-base balance is so important because it is the environment that we play within. So for all of the physical reactions to occur, right? All of the electron transport, all of the hydrogen manipulation, everything that is basically like, positive and negative. How should we say this? So basically, the way that we move energy around in the system is contingent on all of these little physics reactions to happen. And in order for that to happen the right way, we have to be in the right pH. Otherwise, we skew the way that works. This is where people talk about inflammation and being acidic and all of these things, where we're basically seeing an environment set up where it's not as easy for our body to do the normal processes anymore. But it all still kind of comes back to the quality of function in this system. Okay. All right. Reproductive behavior, this part is included as well. So all of the sexual organ function is kind of like also controlled within this autonomic component. Obviously, that is not as dire in the day-to-day, like ambulating around the world, but in the broad scale of like, keeping the species on the planet, it's pretty useful tool. And then the last part is one that actually probably gets a lot more press than a lot of these other ones are defensive behaviors. And we talk about these through the language of fight or flight, rest and digest, like all of these things that are like activation of energy. And I think the reason those get lumped together is because the things that you want to move the quickest for are the things that guarantee your survival. Okay. So, priority probably number one or two is like stay alive. So, if there's something that threatens your stay aliveness, then we want to be able to mobilize energy quickly to be able to use our stay alive tools and continue that job. So when you think about the autonomic system and all of these other pieces where we're talking about basically collecting everything that can create energy and then implementing that process, to be able to do that faster is really useful if you're trying to stay alive, right? So that's where these defense behaviors come in. But I don't want to think about it so much as everything is a continuum of threat. I don't think that that is as useful way to think about it as much as everything is a continuum of energy need. So things that are threatening require more energy quickly than things that are non-threatening. And that is probably a more useful way to put these together. T, you're doing a great job of like trying to keep the face neutral, looking interested. I appreciate that. Anything to add to our kind of our simple breakdown here of short-term control?
Well, I think like I really appreciate how well you are simplifying what can be like seemingly complex. So, yeah, I think we're doing a great job. I'm liking what you're throwing down here. And yeah, let's keep it moving.
All right, move it we shall. Thanks for the inputs there. I do see you guys have some questions. We'll be getting back to it. Um, but I think this is important. We're going to rock and roll. Let me see if I can get the next one up here. And by the way, just for those of you guys reading along at home, you can see the reference at the bottom of the screen here. It's way down there in this one. But you might recognize the book, Wilfred Janig, Integrative Action of the Autonomic Nervous System. Subtitle, Neurobiology of Homeostasis. One of the best books on the planet. What I'm going to do is I'm going to get Tenny to come build me some shelves back here. We're going to do a little team building exercise. We're going to build some shelves and we're going to put that book like right here over my, like the angel on my shoulder. Okay. Because it's a wonderful book.
Okay.
Okay. We got it. All right. Let's go to long-term stuff. Thinking long term. This is the Bitcoin of the world. Long time preference. Here we go. So, recovery. These are circadian. So everybody talks about circadian rhythms. They are wonderful. You guys should know all about them. They are the things that basically travel on a frequency that comes with a turnaround of the planet, right? So every time we get a little quick spin one day, those are the things we want to see. So sleep and wakefulness are the big ones, but these also have to do with digestion rhythms, with the rhythms of, well, we're probably going to see these here. Maintenance of body organs and tissues. So the way we actually like, repair damaged tissue, not even damaged, but maybe senescent tissue, just getting old tissue. We want to freshen it up, bring some new cells in, liven the party up a little bit. Okay. And then at a cellular and systems level, it's protection. So this is the continuation of that kind of defense response, but also the continuation of just the simple regulation of digestive tract, the blood-brain barrier, basically the whole arterial integrity. Like how good is our Great Wall of China that separates all of the things that are from the external and allows them to come into the internal. Okay. So inflammatory processes are a big deal. I don't know if a lot of people recognize that immune control is a subset of autonomic control. So even when you look into the brain, in the insular cortex, in the cingulate gyrus, where we have kind of the primary immune outputs, these are autonomic areas in the brain. So it's pretty cool. Pretty slick stuff. Okay. So those are that's basics, right? So that is like really really simply thinking about it, what is the autonomic system in charge of? And if you can just kind of think about it like that, it becomes in charge of energy, like energy distribution and acquisition. And then, but also on the waste end, but then also on the recovery end. So, how do we use that energy to rebuild ourselves? And I think that I wanted to make this point because in the rehab setting, a lot of energy is actually, so we perceive a lot of energy as inputs into the system in the form of whatever exercise we're doing, right? Whatever rehab you're doing. But what also needs to happen, and maybe more importantly, is we need the systems that are in charge of recovery to be able to start to increase their capacity and their demand. So the more we do, can we push that recovery system so that it can tolerate more inputs, that it can handle, that it can heal, that it can fix up overnight. And so when Dr. Tenney showed that imagery today, I look at that as like check mark, sweet, we can at least solve the problem of distribution. We're getting blood to the places it needs to go. It's oxygenated, it's got glucose, fantastic. Now that gives us the environment to then let this person sleep, let them start to recover so that as we push them, they are actually able to start recovering in a way that they weren't able to do before. So the knife's edge of that is that I don't expect people, once we solve that part of the problem, to instantly feel better. What I expect is that now we can actually start leaning on this system to push it in a way that it can also recover on the back end. And I think that part gets lost because you just like get so like excited and hopeful. But the important part is now all of this background of being able to manage energy starts to become functional, becomes utilitarian again. Cool. Ritvig, hello. Good to see
Mhm.
you. All right, let's rock and roll. Okay, so now we'll just talk about real quick the differences between sympathetic systems and parasympathetic systems. What do you think?
Mhm.
Game time?
Yeah.
Let's do it. All right, have you guys heard of this term, effector cells? Dr. T, how would you describe an effector cell?
Well, they are well, we
I would
have
use the term like the end point. So, like
yeah,
the last thing in the chain, in the neurological chain that then creates the movement, right? So, like, where is something
yes, they
having its
are
effect?
yes,
Fair?
fair.
Okay. Fair. Love it. Okay, so the effector cells and the organs of the sympathetic nervous system, let's differentiate them from the effector cells of the parasympathetic system. Cool. Really way to think about the sympathetic system is it's smooth muscle. What is smooth muscle? Smooth muscle is all the muscle that isn't like your skeletal muscles, like the stuff you flex in the mirror, skeletal muscle, striated muscle. All the stuff that's organs and glands and like working in the background, all the boring stuff, smooth muscles. Okay, they're the ones that are in the organs. Cool. So, what do we got? Blood vessels. We talk about this from time to time, right, T? We've been known to share some words about blood vessels.
Yeah.
Those are in the team. So, the sympathetic nervous system controls the smooth muscle in the blood vessels. Also, the erector pili muscles. What are those? Those are your little hairs standing on end, your goosebumps
Yes.
when,
Mhm.
right? Goosebumps. So the ability to put that hair on end, increase the surface area, increases our ability to have sensory inputs, right? So if the
Mhm.
hairs stand up, it increases the amount that I can feel. So it makes me be able to be more, have more sensory acuity. We got pupil activity. So the sympathetic nervous system is going to be in charge of pulling the muscles that open up that pupil, that dilate the pupil. And then we've got lung activity. So the ability to control. It's wild. You guys might not think about this, but inside your lungs, depending on how much exchange needs to happen, we actually like change the structure of the lung so that it's able to either pull out more oxygen or less. So it like gives it more surface area or less surface area, which is pretty cool. So our ability to just breathe normally is dependent upon the sympathetic nervous system to be able to modify that tissue in the lungs, which is pretty cool. Evacuative organs, so bladder and bowels is a good way to think about that on the large scale. And then also glands will have a different type of release, but that's a different thing. Sphincters of the gastrointestinal tract. So this is just like the little compartment separators within the tract of the gut. So you got your stomach that transitions to the small intestine, that transitions to the large intestine. Why do they all matter? Why are they all shaped differently? They all have different jobs in the sequence of digestion, right? So the stomach does a little different job than the small intestine, does a little different job than the large intestine, does a little different job than the rectum, right? And they absorb different things. They have different barrier systems. And so they have to have different pHs as well. So the internal pH of those systems is slightly different between them, which is why um, some of the different GI infections are when we see the right pH for one area migrates into a different part of the tube, says, hello, I'd like to populate over here. And it's the wrong pH for that system. And then we see things like SIBO or different types of infections in the gut when the pH changes. New organisms grow, problems result. They all have to keep their own pH. Stay in your own lane. Okay? Heart, sweet. So the sympathetic nervous system controls the muscle of the heart. We love that. And then some of the glands. So we've got sweat glands, one type of salivary glands, some of the digestive processes, which are kind of cool. And then I snuck this little picture in there. Can you guys see it? I think we can see most of it. But this is like a really simple chart of, well, I guess you can't see the spine. Let me do this real quick. So this is just a really simple picture of like, these are the segments of the spine. If you could go to chiropractic school or med school, then you've seen these like crazy. But it's like where the nerve comes out of the spine, and then where does that go to affect these different organ systems. You can look at this, take a shot of it. What I think is actually the coolest part is if you look at this like yellow netting here. Can you guys see that? This is on a kind of this is the blood vessel that's traveling right down the middle of your spine. Okay. And this is like the big trunk of blood vessels that gets distributed out through the gut. And what you'll notice, and I think that this picture it captures it really well, which is why I use it, is this net of yellow on this thing are the nerves. So one of the things that was most shocking for me was when you look at this, you see that as you look at these big systems of blood vessels that go and travel through the body, they're just netted with all of these nerves. And it makes you realize like, oh, that sympathetic system is like tailor made to go everywhere these blood vessels go. And you see these big nodes, like these big yellow balls, this is celiac ganglion, right? And the aortic plexus and the inferior hypogastric plexus, like these little nodes. These are all little command centers that help us with reflexes for these nerves, right? But see how they happen at these big bifurcations? Like you see where an artery is about to have an exit ramp? We have these little ganglion and these plexi at these areas, right? Super slick. And so the magic in that, like you want to talk about erector pili, the goosebumps that come with this are when you realize when we talk about that sympathetic system, it's really, 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 really important for being able to shunt that blood through the body, for being really discreet about it, right? So I can do the different math and I can do the soccer. I can do those different things because we have this system. If we didn't have it, we would be like a worm. We would be like a one-trick pony. We can do one thing. But because we can do so many, or the reason we can do so many things, one of them is that we have this distribution of systems that allows us to take one brain and to separately control all of these different blood vessels simultaneously, same time, but specifically so that we're getting it to the right spot. Pretty cool, right? And I think this is just magic, but it's also the reason why why I talk about it all the dang time is because once we lose just like a bit of control of this thing, it can go south quick because I've got all this blood that's supposed to be distributed through this gut. And then if I don't do a good job, it just kind of like it's going to go to gravity. So it's not like it just returns home back to the heart and waits for where to go. It's just going to kind of settle. And when it settles, it doesn't get back to the heart as easily. And now I've created a problem of being able to be upright and actually like continue that fuel process in the brain. So super, super important. And then we've got all of these little corollary ones that are going to go to the organs that help to manage how active these organs need to be in order to maintain this stable energy supply based on the system that we are in. Okay. So I hope that that's useful. And I'm trying to do it in a way that is tangible to take home. If we were in a class, it would be dangerous because we'd have another 8 or 10 hours of this, but I'm going to cut it there. And we're going to talk about the other side of this common coin. We're going to talk about the parasympathetic system. Okay. This is not the archenemy of the sympathetic system. They're just shaped differently because they serve a different purpose. So the one we just looked at, all those nodes are really close to the spine, and then we got all those nerves that branch out from there. So it's like the control system's really close to the central nervous system, and then we get all the branches that go out. Okay. And then the parasympathetic system is kind of the opposite because these guys are in charge of different things. They're in charge of the exocrine glands of the head, basically stuff that secretes stuff in the head. So your salivary glands are a good choice to think about for that one. Okay, the intraocular smooth muscles. Again, we start to think about the pupils here. Okay, the smooth muscles and glands of the airway. All right, so we talked about how the sympathetic system is going to help with oxygen exchange in the lung, but then we've got another component in the airway itself that this is where like asthma comes in, right? So where we get an overreaction and we see that we get like an inflammatory response within those smooth muscles in the glands. So in order to kind of set the nature of that airway, we rely on a constant stimulus from the parasympathetic system to maintain kind of the mucous membrane, keep everything pliable, bendy, lubricated, all that good stuff. Okay. And then same thing, smooth muscles and exocrine glands and endocrine glands in the gut, featuring the enteric nervous system, which we can talk about a little bit as well. Now here we see also, oh shoot, we got another thing, we got another heart list, right? So interesting. We've got sympathetic and parasympathetic innervation that both go to the heart. We got to talk about this because it's going to fly in the face of another thing I'm going to tell you. Okay. And then the pelvic organs, the urinary tract, hindgut, and then reproductive organs as well. Okay. And then this one, the epithelial tissue and everything that has like a mucous membrane, a mucosal system, it's in charge of keeping those secretions stable so you don't produce too much and you don't produce too little. So you don't want to have your throat be dry, but you also don't want to be hacking up all the time, right? So that sweet spot is what helps us to be able to manage some of that immunology and keep our barrier systems intact. Like it's just like the same way you'd put lotion on your skin. You want the same thing to happen on all the internal stuff too. Cool. Now let's get the exceptions. All right, so it doesn't supply the helical arteries and sinusoids of erectile tissue of reproductive organs. Different game. Okay, there are some intracranial, uterine, and facial blood vessels that are involved. And then the blood vessels in the salivary glands, which is very interesting because those are like on an island. Okay. All right. This is one of my favorites because it's one that I get people that have been physicians for 30 years and they've never thought about. The parasympathetic system doesn't have any innervation of the blood vessels in somatic tissues, like in the body, nor in the viscera, in the organs. Okay. So that part's wild. So the parasympathetic system is out. And that's why it's important. We have the conversation around like, I did a podcast yesterday with John Chung, good friend of mine, great guy, good teacher. And we talked about this because we talk about vagus nerve stimulators and one of the presuppositions of that tool is that it just counteracts whatever the sympathetic system does. And that's just not the way it works, right? So, and you can see that here. The thing that we were most concerned about with getting blood into the head is like, can we move it there? And we actually see that the parasympathetic system isn't really involved in a major way in the control of the vascular component of that. So if you know that, then you go, that's going to change the way I treat this sucker by a lot. So it is not involved in blood pressure regulation, but there are specific effector vessels that it is responsible for. So there's only two spots where there's target tissues where we've got this. We've got the pupil to talk about, and we got the heart. But it's not as though they are antagonistic to each other. So it's not one and then the obvious, or excuse me, one and then the other. We see that these systems actually work together. They're synergistic. And even though they may exert influence over the heart or the pupils, it does it under different conditions. And the easiest one, well, there's two. So when you think about the pupil, I don't know if you guys can see this, but you got two pupil options here. What do you think, Dr. T? Those look good?
Yeah, they're a little small, but we got them.
All right. So you got two options. You can kind of like dilate them so you can make that pupil bigger, or you can make it smaller, right? But it isn't that it just like contracts and then relaxes. There's two different types of muscles here. We've got ones that kind of look like spokes that go around the outside, and on the inside there's one
Mhm.
that's like a sphincter, almost like if you think about like the zoom on a camera where it kind of twists like this, and when it contracts, it can pull closed. So to dilate the pupil, the ones that look like spokes, they pull, just like a puppet strings. They pull it and make it bigger. And then they can kind of relax it back to, their normal. And then if I want to constrict it, I take the ones on the inside and I twist them like that and I can make it smaller. So they're actually two different things. And what's interesting is we can go into a lot of depth on how our pupils will actually change based on not just like if you're scared or not, but actually what you're looking at, your object of regard, what you're focusing on, how far it is away, how much light should be coming in to keep it clear. So anybody who's like, I've been having to learn Nomad over normal has helped me a ton, but like how to operate a dang camera and get the light to be right. So if you use too much light, I look like a ghost. And if I use not enough light, it looks like I'm trying to be mysterious. So like somewhere in the middle is where you got to live. And that's like what your pupil's job is to kind of figure out what is the right amount so that you can see clearly, right? So even though we have a sympathetic effector and a parasympathetic effector, we're actually using them in kind of like different tasks to be able to manage this pupil, which is really slick. And I could talk for days about that. It's really neat, especially like changing the way you think about things, like thought, fatigue levels. All these things can modify this. Anyway, the other one changes in the heart rate. So you get traffic to your heart from both parasympathetic and sympathetic nerves, right? That's pretty cool. They go to a place called the cardiac plexus. Oh, Dr. Polly in the house. Love that. Sweet. Good to see you. Okay, so if you talk about the heart rate, this is really part and parcel to this group. That's why we're talking about it. During changes in body position, emotional stress are generated via changes in activity of parasympathetic neurons, the pacemaker cells. So fast changes in the heart rate during these positions, right? The sustained increase of heart rate during exercise is mainly generated by activation of sympathetic neurons. So what does this mean? Let's do it. Um, I'll come back to that part. Oh, I thought I had another image there. Let me pull that back up. Apologies. I thought I had an image to go with this, but I don't. So think about it like this. Your heart has like a set rate that it wants to beat at. Anybody that's had kids or has seen an ultrasound, a little belly ultrasound, you might have noticed that a kiddo's heartbeat beats much faster than an adult's heartbeat. Even like my little kids, my 6-year-old, right? Her heartbeat is a little bit faster. Why does that happen? So the resting rate of the heart is kind of like somewhere between 100 and 120-ish, right? That's where it wants to be with no brain connected. And then once you start attaching the brain to it, what the brain does is it uses that parasympathetic output and it slows it down. And the more efficient it is to do that, the slower it can be. So if you can imagine, your efficiency of maintaining blood pressure is a function of like, well, not, no, your heart rate is a function of how well you maintain blood pressure. So if I'm really efficient at it, I don't have to beat my heart as much to maintain pressure, which is pretty cool. And so I can have that parasympathetic system slow my heart down even more because that uses less energy and it's more efficient for my body, which is pretty great. Now, if I want to like get up real quick, I don't have to really do a lot to like hammer down and hit the gas pedal and get the sympathetic system going. I don't really have to do that. All I can do is just let off the brakes of the parasympathetic system, and that heart will be like, let me run, and it'll start to raise up toward that 100 to 120 mark, right? Which is pretty cool. Cool. So in that range, like 100 to 120, I don't really have to do much. That I just back off the parasympathetic inhibition, and that heart rate will naturally climb up into that range. Okay. Then if I want to crank, I'm back on the soccer field again, and I want to take it even above that 120 mark. Now I can shift over and I can push in that sympathetic drive. And now I can have that heart crank even more, which allows me to take it up from that like 120 range up into the 170 range, let's call it. So if we think about somebody with POTS, when I'm looking at them, there's a difference between somebody who, when they pop up, is going from, 70 to 120. That's still 50 points different, right? So it's still a big jump. But there's a little different physiology happening than if they take it to 150. Because now I've had to introduce a new signal to the mix, right? So I've had to do a different physiology to get there. And those things they seem subtle and they're like, oh, cool. But they really matter in terms of like how your body is trying to solve for this problem and to what end. Same thing if my heart rate starts at, if it's cruising around 100, then I know that that is a very different thing than if it starts at 65, 70. It means that like my ability to provide that inhibition to the heart is either not working or my brain has decided that we shouldn't do that in order to maintain the state that we are in. Fair enough? Okay, so at the end of it, what are the basics here? The autonomic system really comes down to energy. It's how do we make it? How do we mobilize it? And how do we make it efficient and recoverable so that when we expend energy, then we can also replenish the system that allows us to recover quickly so we can spend it again. And that would be like, I would move people away from thinking about it in terms of rest and digest and fight or flight, and I would move it toward thinking about it in terms of how much energy am I using? Is that efficient? So if I'm cranking 120 just to like eat an orange on the couch, that's not efficient. And so then we have to back out of like, well, why does my body have to do that to be able to maintain this status? Are there things that I can do so that my body can be more efficient, so that I'm not burning all of this energy in order to do really simple tasks? Cool. Okay, Dr. T, fill us in here,
Mhm.
bring us home. That's my part, and then we'll do some questions.
Yeah, I think you did a really great job there. Yeah. Woohoo. Yeah, one of my most favorite topics. I'm super glad we were able to kind of just break down autonomics and um I think it's important. I know you know how important it is to keep like on the horn about how parasympathetic and sympathetic isn't necessarily just this teeter-totter on and off system. So, yeah, hopefully this is like a little like snippet into understanding how these systems work and how we can work with them moving forward in a clinical setting.
Oh, there we go.
Yeah.
I had to mute it. So I'm going to do some questions. You want to stick around for questions? You taking a nap? What are you up
I
to?
think I'm gonna log off now. So,
I know your
um,
smile's gonna hurt so much tomorrow because you were just like, you gotta like be on there. It reminds me of the people when you see them on the news and they're just sitting in a room by themselves and Just trying not to do that. You did wonderfully.
I mean, I kind of
So
have a smile on all day, so
that's true.
I'm
You've had a
used
lot
to
of practice.
it.
Thanks
Okay,
for
well,
coming on.
yes.
Thanks for introducing yourself to the team here.
Yeah.
And we will see you tomorrow.
All right. Yeah. Loved seeing all these comments in here. And yeah, we'll see you guys next time.
All right. Wish us luck. We're going to try to answer a few of them. Okay, team. Super great of her to come. She was a little nervous. Don't tell her that I told you. Um, but super happy to have her on the team and working really, really hard. And it shows. I'm going to tackle this conversation that I'm seeing with started with Ritvik. He said, Ritvik. Let me see if I can pull this up here. I don't know why I'm not able to pull them up. Okay, so I just have to read it. He says, hey, doc, do you get patients whose sympathetic system is so activated by the exertion of the travel to come to your clinic that's a challenge to treat them? If yes, how do you tackle that? Actually, that on the face of it seems like it would always be a problem for everyone forever, right? And it is not easy. Travel, I wouldn't say, is an easy thing. Obviously, we get patients every single week of the year, minus the ones that we take off for rest, that come from somewhere else on the planet. They are not local. We see very few local cases, and everybody who's in the clinic right now would attest to that, um, which is great. And it would be better if they had someone near them, but that's beside the point. So, do we find that it is difficult based on the travel alone? Not so much. We actually find that the travel itself can be part of the learning process for like where we are in a capacity range. So some people, um, it, what I would say is there are a lot of people that don't do as bad as they think they will do when they travel. Just it's been so long and life has sucked for a while. And they actually find that the travel wasn't as bad as they thought. Other people, it is as bad as they thought, and it's not great. But either way, it gets us to a point where we get to observe what's going on, and then we work our way out of it. And that's the job, right? So, like, we don't want to show up pristine. We want to show up and see like what doesn't work, and then how do we break out of it? Because if we can break out of that, then like there's a lot of momentum in the right direction. So that's actually not a thing that is actually such a big deal. Although on the front end, before you get on the trip, it is a big deal. And there are people that, have a harder time. They got to take a couple days to get here. They got to like get their act together when they get here. Totally reasonable, totally doable. Um, but it's just kind of like part of this time that we're in where, um, we're not so fortunate that there is a specialist in every geography, though I would love there to be. But it's also wonderful that we are not as limited as by geography as we had been in the past. I was talking to someone today about this in the clinic where it's like in the last, I don't know, decade, 20 years has been the first time really that you could go in on your own, really investigate in a profound way your own health and your own health challenges, and then to be able to interface with people that have insights in those fields. Before that, you'd had to write letters or go visit a university, and you were kind of limited. You were kind of limited by, man, I hope someone knows a lot about this near me. Otherwise, it would be really hard to figure out who to turn to. And so I would, it's pretty amazing though that we have this ability to be able to seek out help, whether it's in health or anything else, across geographies now in a way that is was pretty remarkable. So yes, I understand completely the concern about travel, but I've also seen a lot of people make journeys that would surprise you. Right, our good friend Chris, 8 years on the floor, basically, right? I'm not overstating that. Um, First time, flight outside a country, going to come to the U.S. to come, to come here. Um, there's a certain amount of bravery and risk that come with that. So I would just want to encourage people. I know to travel is tough, and yeah, and then we do it anyway, so we can figure out how to fix it. And so that would be my statement on it. Obviously, I'm not the one doing the traveling, but a lot of people do it, and a lot of people on here could talk to you about that. Okay. Ooh, big Erm, 3 years on the wait list. That's ridiculous. That's Toronto. Well, you guys know how I feel about that. Okay. Let me see. Ginny has thrown some of these old ones in the chat for me. Not old, earlier in the role where I'm behind. So let's see where we're at. We'll take a few. Hopefully you guys are doing well tonight. If you could do me a favor and give me some feedback on kind of the little educational snippets at the front end, just let me know, plus or minus, good or bad, just how you feel about them. Do I need, how would you want me to improve them, do it better, all those things. I appreciate that. Okay, the traditional tilt test, I think Dr. T answered that one. How do you differentiate CCI, craniocervical instability, from CFS and PCS? Or so that would be like chronic fatigue and post-concussion. Okay, so I think this is a good topic. Hold on one second. Fat Matt, I don't mean to tease you on that here real quick, but let's see. Okay, you can display them like that. That's not what I was trying to do. So Mathieson had said that the share was you can request a wheelchair assistance in the airport. You don't have to document why. They will you to your gate, so not required to walk in the airport for sure. You can request being taken to the gate, being brought out to the car, hopping in the car, all that stuff. So yeah, good feedback. Just let the airline know what you're doing, that you're traveling, and then maybe some people in here that have done it might have other things that are useful. I try not to get too much into that because I don't want to talk about because I've never had to do that travel, not like in your shoes. So those tips I'm not as good at those tips, but man, we've had a ton of people travel, so maybe we can reach out and we can do a little crowdsourcing on that. Okay, Fat Matt. How do you differentiate CCI, craniocervical instability, from CFS, chronic fatigue syndrome, post-concussion syndrome? And it's also complicated. And it is when you look at it through those lenses. If you look at all of these, well, not all of them, but if you look at particularly the ones with the S's on the ends, the syndromes, these are collections of symptoms. Now, craniocervical instability is a thing that you can measure. Chronic fatigue syndrome, not such an easy thing to measure, right? Because you're just collecting symptoms and lumping them into a category. PCS, you're kind of lumping symptoms and creating a category. So in both of these scenarios, what I think is more useful is moving away from trying to decide. It's kind of like trying to organize yourself by what shirt everybody's wearing. The syndrome nomenclature isn't really that useful because you have a lot of different syndromes that have similar overlapping symptoms in them, but they have different causes or different catalysts. And those are the things become important because the mechanism of why is more important than the symptoms themselves. So why are the symptoms there is a better question to ask and answer than do I feel them and how do I feel them? Like, what are my feels? So my advice on that would be you really want to move toward a diagnostic process that takes you out of the syndrome and into the mechanism. So for example, if you've got CFS, well, we know two of the tests you got to look at right away are transcranial Doppler on a tilt and end-tidal capnography. We know huge percentage of cases, 90 plus in the cerebral hypoperfusion case and 70 plus in the hypocapnia case. Like those things are both true in CFS. And then you can try to figure out, well, where do those come from? To what degree are we having mitochondrial deficit? Can I measure lactate? Can I measure CoQ10 outputs? Can we start to get a handle on like where is the actual problem? A lot of time we just make an assumption that there's a problem, right? So we go to the MECFS forum and they say everybody's got a mitochondrial problem, and then we just kind of assume that's true. But then if you go and look at the mitochondrial papers and you look for the IL-6 and the IL-8, you realize that like 40% of people don't express them at all. So if almost half of the group doesn't express the inflammatory protein, then we can't say that it's inflammatory is the causality. And then we can't know that if it's then that is the cause, or if that's the ambulance showing up at the accident. So there's all these pieces, right? But you can then start to at least identify where the causality is. PCS, do I have normal vestibular function? I can measure my eye movements. I can see if they're doing the thing we expect them to do. I can measure my reflexes. I can see if they do the things they're supposed to do. I can do cognitive tests, see if it does the things we're supposed to do. And then I can try to work towards solving those problems. And I think that that is a more useful orientation that will get you further. Now the CCI, that's a little bit different because that instability you can measure, and you can measure if in that instability it reproduces symptoms, right? So if I'm in a DMX, a digital motion X-ray, and I'm finding that I get more movement of my, my alar ligaments, then I want to see, like, can I induce problems? Can I induce problems with physiology, problems with outputs in those positions that would replicate my symptoms? And now I have a place to go from. So in all of these, there's a way to provoke the system in a way that can bring out the symptoms, and we can understand where do they come from. And so that would be my approach for differentiation, rather than trying to see which one you check more boxes in terms of how you feel. I don't really like that as a mechanism. Hope it helps. Okay, Halisa. Whoa. That's the same. Well, I don't know if that's different or not. Virginia. Okay, Sasha, is that a significant of a drop of heart rate on the second round tilt common? Yeah, it's just normalization. So your heart rate is just cranking up like you're exercising. It doesn't know the difference. So if you're getting drops in cerebral blood flow for this particular case, that's the way they compensated for it. And we see CO2 levels change. We see all of that compensate for the lack of blood in the head when you stand up. But if you can get the blood there, the system's more efficient, then the heart rate will just naturally kind of move down again, which is pretty slick. Doru asked, what do we do to help her improve? So in this particular case, we're looking at doing kind of a correlate effort. So it's not one thing. It's a combination of eye head stimulus, so coordinating eye head movement, but also with proprioceptive stimulation through like neck afferents while we're creating that movement, so that we kind of orient to our head better. So underneath this is where we're seeing this proprioceptive error in the control of head and neck function. And just said simply, and by recalibrating for that, improving that signal ratio, then the brain's actually able to organize blood flow better. And so it controls it better. So the way to think about it, it's harder to talk about in blood pressure terms because that's a harder motor pattern. But the same way you could take someone that might have a problem with like accurately putting, their finger on your nose or pinning the tail on the donkey. But by training the brain so they understand where their hand is better, then it makes it way easier to do that task, right? So same idea. We want to make sure that we're understanding where we are. And part of the benefit of that output is that it's tied to the reflexes of our autonomic outputs. So that's just kind of a quick synopsis of that. Jesse asks, does norepinephrine raise normal for some people with POTS? Is it normal? I'm going to assume the question here is it normal for epinephrine to go up with people in POTS? So norepinephrine, we just talked about sympathetic nerves, right? So norepinephrine is what that nerve uses at the end. So we send an electrical signal from one end of the nerve to the other. And then at the end of that, it releases a little chemical to the next nerve, and that starts the electricity at the next nerve, and then it goes. So that chemical that gets released where those two nerves butt up against each other, in a sympathetic nerve, that one's called norepinephrine. So it really only exists in this little cleft right here. But if you have to really crank that out in order to maintain blood flow to your head, then you're going to have more production or more utilization of norepinephrine at that nerve ending that we can measure, and then you can see that go up. The thing that confuses people sometimes, though, is we think of norepinephrine as the same thing as epinephrine, and then that's, or adrenaline that's produced in the adrenal glands, and they're not the same. It's a similar name. It's confusing, but it's not the same. One is a metabolic hormone, helps us to be able to release glucose better. So it helps us pull glucose out of the liver, out of the muscles, out of the blood supply, and helps us to be able to use glucose. Whereas norepinephrine goes between those two nerve endings so that one sympathetic nerve can talk to the next one in the line. Okay, so those are the difference. And they can go up and they should go up if we're seeing an acceleration of vasoconstriction, if we're seeing increases in heart rate, if we're seeing changes in respiration, right? We talked about that lung activity. So all of those things may possibly yield higher levels of norepinephrine simply because you're trying to crank it out more. Just like if you were stomping on the gas pedal and you had more exhaust coming out of the tailpipe because you're burning more. So that might be a good way to think about it, Jesse. I love this name. Banana Wolf. How can I prove it's not FND when I have a positive tilt table test? Interesting. There might be more to that question. There are a lot of people that have this crossover between an FND diagnosis and a cerebral hypoperfusion diagnosis, where they have positive tilt findings, but they also have functional neurological disorder or functional movement disorder. And these become very tricky in a conventional world because people don't know how to put that in your brain very well. What I would say, though, is um, you don't want to prove something's not FND. You want to actually have to prove that it is FND. And there are criteria for that. And they're published and sometimes they're ignored. But based on the distractibility, based on the fatigability, based on the frequency, the spreading. So there are ways that we do kind of specific tests to look at whether or not something is considered FND or not. But there is a correlate between people that experience that and these positive tilt findings, especially around hypoperfusion. So you really want to prove like that it is FND, and if it is, that's fine. Doesn't mean anything. Like it's not a. Unfortunately, it's a diagnosis that isn't given very well because it for some it implies that it's like a choice that you're making, and that's not the case. You just want to use it for what it is and be able to get to the outcome to be able to solve for that. Okay. All right. How do wearable monitors like smartwatches impact the autonomic system? Seems like I can't keep my phone in my pocket. I shouldn't wear a watch 24/7. Yeah. So for the people that pay attention to radio frequencies, to electromagnetic frequencies, wearables are probably a no-no, right? So if you're taking the step where you're not putting your phone in your pocket, you're turning on Wi-Fi mode, you're trying to reduce your exposure to radio frequencies or to microwave frequencies, which can be useful, then you're probably not going to want to use a wearable because you're just going to amplify that. Same with like AirPods are an example of that too. You're running a Bluetooth signal right between your ears, right up next to your brain. I don't, if that means anything to anyone else. It's not a it's tough because there's so many things to worry about. When you add that in, it gets wild. But taking the adventure down, looking into EMF and radio frequencies might be useful for some of you. Keep in mind that you can change the things you can change, some things you can't, or you can move where you are. But you make some legitimate life decisions once you start noticing these things. So caution in that sense. But it is a thing that we're contending with in this time of life. Okay. And I can talk about that more if you want, but it can feel a little overwhelming. So I try to take it in small doses. Okay. Dual tasking, what does it mean? So a dual task is basically a term that we use to describe a cognitive task that is coupled to another context. So we may do it when people are walking or when they're doing a certain manual task, or in this case, when they're on a tilt test. We don't always tell you what they are because we don't want you to try to prepare for them, but it's just a mental task, a cognitive task that we have you do so that we can see when you're trying to think, does the system respond the same way or does it change? And that part's what we're looking at here. So when you saw the case we looked at today, the cerebral perfusion went up during the dual task, which is great because it means when the brain demanded more energy, the body was able to fulfill that demand, which is fantastic. And one of the things that really helped in this case. But in some cases, when you go to do that, we actually see it drop. And in these sense, we know that the metabolic capacity is not as good. Um, are there any options for people at home to monitor without wearables? You'll have to do manual recordings. And it depends on what you're trying to measure, I suppose, too, or if it's valuable to measure any of these things. Those would be the first two questions. But to measure like heart rate, blood pressure, just simple pulse ox or an automated blood pressure cuff, those things are reasonable. It's mostly stuff that is like transmitting to your phone or getting a constant signal all the time. That if that's something you're concerned about, then you may not want to do that. Okay. Okay. Let's see. Oh, that's a good name. Mom on the Fly. My son is stuck in a flare. I'm sorry. Stats sitting one blood pressure is 148 over 88, 66. I'm assuming that's heart rate. Standing at a minute, 127 over 89, 95. Standing 3 minutes, 132 over 93, heart rate 98. We no longer know what to do for him, what medicine he needs. You got to get a better workup. Going just on this is probably insufficient. Um, and I'll give you a couple of reasons why. Number one, sitting to standing isn't as useful as laying down to standing. Standing after 3 minutes is maybe not as helpful either. And then we just need more variables and then more history. You got to do a deep dive here. You got to figure out how did we end up here. So you're doing a rewind back through, and how you end up here informs a lot of like what you do to get out of it. But based on just these numbers, you can't know what the initial catalyst was or how to start to unwind it. But with more information, I think that's probably definitely something worth doing for him. So good luck, good luck, good luck, good luck. Banana Wolf. Can I ask you where that name comes from? Because it's a fantastic name. It's fun to say. It's fun to read. Wonder what it means. How do I get doctors to take me seriously? I become catatonic when cannot intervene in an episode. I fall often, dizziness, nausea and vomit, fatigue, brain fog, weakness. Probably the same advice here too. I mean, I can't give great advice as far as like actionable medical advice. We don't do that on the internet or in live streams. But how do you get them to take you seriously? I mean, this happens a lot, especially when you're in an episode, you're like gone. You're not able to like just carry on a normal conversation. So it might be useful to try to preempt that and provide them with the communication beforehand. And then it just depends on the listening quality of the person you're talking to too. So it's, are they taking the time to actually like sit and listen or read about you or investigate what's going on, or are we just trying to get you to the next person? Unfortunately, if it's the latter, we're just trying to get you to the next person. That's what they're going to try to do no matter what. Like they're just going to try to get you to the next one. So we got to get you in front of somebody who is thoughtful and wants to be there in the shoes to try to help. Okay. All right, Genia. What do you think? All right. Shannon says, thanks for the education. I appreciate that. Added to the playlist from Redpick. John Lane, interesting that it would be anhedonia and memory issues from suspected CCI. You might want to dive into that a little bit more if that is the full symptom complaint, and then looking at CCI, there may be maybe more workup to do there. Okay. Again, going back to my travelers, I wish you guys all the best in that, and I want to see you do it, honestly. What is a silly question? If you were a vet, oh, interesting. Vic. Okay, if you're a vet and had to treat POTS in a giraffe, how would you go about it? Would there be any difference from the way you would treat a human? I ask as a human with a long neck. I understand. This is a point I think Blair Grubb made one of these points in one of his papers. if I can remember. Anyway, how would I change it if it was a long neck? So if you are someone who has existed in a life where you had normal activity with your long neck, and then subsequently had a period of time where you are no longer able to function normally with your long neck, in order for me to treat it differently based on the long neck, something would have to change in that long neck that would warrant that investigation, right? So if we say that a different way, if it had the capacity to be normal within that system, then we actually want to see like what caused us to deviate from normal, and is that something that we can correct for and trend it back toward that. The length of neck isn't something that I normally think about as being a major deterrent. Like I don't measure people's neck lengths and be like, anything over 11, I can't help you. Um, it's more in terms of where have we been and where are we now. If you're somebody that was like a lot of, if you're an athlete and then something happens, you get sick, and then you're not doing as well, we're probably not going to blame that on the old long neck. Although I like where you're going with this. So you just want to look at the function. Does it move correctly? Do we get proprioceptive demand correctly? Does it transmit fluids correctly? If does it move in dynamic situations correctly? Is it coupled to the eyes? Is it coupled to the inner ear? Um, is it sitting on top of a spinal system that is normally oriented, or do we have postural changes, in the clavicular and rib relationships that cause alterations in path of travel, things going through there. Okay, it's a good question. I like the way you frame them. Okay. Okay. Looks like we got some folks. We got some people coming up the 29th. Big time. Can't wait. We got such a good team in. Can't wait to see more people coming. Great group in this week. We've been having a lot of fun. A lot of good happy party. So I really love it. All right. Okay, back to the EMF question. Who should be concerned about such things? Red light, fasting, more about circadian rhythm. That's what we want to talk about. There's some resources about that. I actually had this conversation today. There are things that are generally good and then sometimes not as specifically useful, and meaning like they may help with some parts of it, but not like get you the whole thing. That's okay. Um, there's some great resources out in the world that talk about these things. Generally speaking, there's a reasonable body of evidence that suggests we should probably limit our exposure to electromagnetic frequencies, to radio frequencies, to any external electrical activity that interferes with our ability to detect the Schumann resonance that comes from the ionosphere out in, outside of the earth, kind of stabilizes our resonance here at around 9.8-ish hertz. So things that deviate from that, like, extremely low frequency waves. These would be things like Wi-Fi, cell phone signals, Bluetooth signals, being near a cell tower, power lines, stuff like that. Those sorts of things seem as though, if you look at the research, like probably not good for us and probably actually trend toward bad. But that's across populations, and that's not necessarily specific to our autonomic cases. So in some ways, everybody probably would be better to go ahead and shut the Wi-Fi down at night. Don't hold your phone on your pocket all the time. If you got to put it in your pocket, put the airplane mode on. Nothing's that pressing. Try not to live near the power lines. Try not to live near the cell phone towers. Be in a position where you can limit these things as much as possible. And those things go a long way. And then you'll do those things. And then for a lot of people, you realize that may not have been the main culprit, but it certainly doesn't make things better. And then you try to solve for the main culprit. Cool. Awesome, awesome, awesome. Okay. It's 9:30. If I go in right now, I can probably give my kids a hug before they go to sleep. So I'm going to go do that. I had a good time talking tonight. I really appreciate you all. I'm probably going to keep doing some teaching on the front end because I want to continue to go. I feel like there's a lot that we haven't talked about that we need to put in our library. So I'm going to keep doing that. Let me know what you think in an honest way, please. And then I'll try to make that work for everybody. So thanks for a great night. Big wins this week. Let's try to put something in the positive column and let's keep going. And I will see you all